Welcome to episode 8 of the Semiconductor Age. Memory has always evolved alongside computing. But as processors become faster and AI demands enormous amounts of data, conventional memory technologies face new challenges. So what will memory look like in the future? Modern processors can perform billions of operations every second. But computation is useful only when data reaches the processor quickly enough. This growing gap between processing speed and memory performance is known as the memory wall, and it is becoming one of computing's biggest challenges. Traditional memory became increasingly difficult to scale by making cells smaller and smaller. 3D NAND changed the strategy. Instead of spreading cells across a surface, engineers stack them vertically, allowing enormous storage capacity within a remarkably small footprint. AI and high-performance computing need enormous amounts of data, delivered at very high speed. High-Bandwidth Memory, or HBM, addresses this challenge by stacking memory and placing it close to the processor. The result is extremely wide data access with much greater bandwidth. AI systems are extraordinarily data-hungry. Training and running large models requires continuous movement of enormous datasets between processors and memory. As a result, the challenge is no longer simply making processors faster. Moving data efficiently has become just as important as processing it. Traditional memory relies heavily on storing electrical charge. But engineers are exploring other physical mechanisms, magnetism, electrical resistance, and changes in material phase. These approaches could create memories that are faster, denser, more energy efficient, or better suited to specialized forms of computing. MRAM, or magnetoresistive RAM, stores information using magnetic states rather than electrical charge. It can be fast, non-volatile, and highly durable. These properties make MRAM particularly interesting for applications where speed, reliability, and data retention are all important. ReRAM, or resistive RAM, stores information by changing the electrical resistance of a material. An electrical pulse can switch the device between different resistance states. Its simple structure, high density, and low power potential make ReRAM an important candidate for future memory and computing systems. Phase change memory, or PCM, uses the physical state of a material to store information. A material can switch between amorphous and crystalline phases, which have different electrical resistance. Here, information is stored not simply as charge, but through a controlled change in the state of matter itself. The most interesting possibility is that memory may eventually do more than store information. In-memory computing brings computation closer to where data resides, reducing costly data movement. This idea could support neuromorphic systems and specialized AI hardware, where memory itself becomes part of the computation. Semiconductor memory is increasingly moving from 2 dimensions into 3. Vertical stacking, through silicon vias, and advanced packaging allow multiple layers to work together. The direction is clear: instead of simply making chips wider, engineers are increasingly making them taller, denser, and more closely integrated. Every bit that is stored, moved, or processed requires energy. As computing scales, especially with AI, data movement can become a major source of power consumption. Future memory must therefore deliver not only greater performance, but more computation and bandwidth with less energy. There will probably never be one perfect memory technology. Computers already combine registers, SRAM, DRAM, flash, and storage, each optimized for a different task. Emerging memories will add even more possibilities. The future is therefore not one universal memory, but an intelligent memory ecosystem. Imagine a memory that is extremely fast, highly dense, non-volatile, energy efficient, inexpensive, durable, and intelligent. That is the ideal. No existing technology achieves all of these properties simultaneously. The challenge for researchers is to bring these competing advantages together. At Physical Sciences Consultorium, we see memory as more than a place to store data. It sits at the intersection of physics, materials science, electronics, computation, and engineering. Understanding how memory evolves means understanding how our technological capabilities evolve, and how scientific research becomes real-world innovation. The future of memory will not be defined by one material or one technology. It will emerge from new physics, new architectures, and smarter ways of moving and processing information. In Episode 9, we'll take the next step, from the transistor to logic gates, and discover how billions of tiny switches become the circuits that make chips compute. If you enjoyed this episode, like, share, and subscribe to Physical Sciences Consultorium, PSC. Your support helps us make complex science accessible and meaningful. Until next time, keep exploring, keep questioning, and keep discovering.